talking about here.
And David, this is David again. I just want to interrupt for 1 second, and then I'll leave it. Did you let Molly know where she can retrieve these and listen to them again if she needs to?
You know, I did not, and let me do that right now, because I remember when I processed this, I wasn't sure whether I had let her know that or not. Let me put...
I'll talk to you later.
Okay, thank you, actually. All right, here is my YouTube channel where I put all of my recorded videos.
Okay.
You'll notice that the title of the video has something to do with what we're talking about, and these two letters are your initials. So in your case, it'll be MD and then the date, 030415.
Perfect.
Okay, so you'll be able to identify any of the videos that you're involved in by looking at this last thing on the title.
Okay.
And I'm going to copy and paste this into the GoToMeeting chat window. Hold on. Go ahead and click on that. Go over to that chat window and click on that link.
Okay, perfect.
Now save that.
Okay.
And that's always where you can find the recording. Now, the recording of your session usually I don't get it on here until like 12 hours after your session. What I normally do is I take all the sessions of the day and process them overnight, because it takes 2 or 3 hours to process each one. For my computer, these GoToMeeting files have to be converted to these YouTube files for you to be able to view them. And then I upload them the following morning and I put them on this channel. So some point in tomorrow morning you'll find your file on here.
Okay, sounds good.
In fact, if I scroll through this, we should find an MD from, there it is.
Yep.
There's the last one we did. And then if you just click on that file, it'll start to play.
Okay, cool.
Okay, so that's my YouTube channel. All right. No, I'm really glad your dad interrupted and said that, because I can remember wondering, I don't know that I've sent you that link.
Yeah, no, I didn't know that, so I really like that. That's cool.
All right, let's go back to 13. If f of x is this, without knowing how that graphs, how can I find the local extrema, or the relative extrema?
Is it by doing the first derivative?
Setting it equal to 0. Remember, this function is going to look something like this. I don't know if I have it in the right spot, but it's an upward parabola, and it only has one relative extrema, and that's its vertex. Okay? What is true about that vertex, or that relative extrema? The slope of the tangent line is 0, by definition. Okay? So, if I take the first derivative of this function and let it equal to 0 and solve for it, I'll figure out where I am on the x-axis, where that extrema occurs. So, what's the first derivative of this?
It is 2x minus 10.
Set that equal to 0. You get x equal 5. So actually my picture was not bad. At x equal 5 was where that thing occurred. I don't know whether I need to move that up or down, but horizontally it's in the right location. So that's all there is. Now, This doesn't say determine whether it's a minimum or a maximum.
Right.
Well, when you start with a quadratic, you only have one or the other. Okay, because I know this is a parabola that opens up, let's examine this a little further. Have you had the first derivative test to determine whether an extrema is a maximum or a minimum?
I don't, let me see. No.
Haven't had that?
No.
All right. Well, let's keep going then. Because all we know then at this point is that at x equal 5, we have a relative extrema. We don't really know if it's a minimum or a maximum, although because I know it's an upward shaping parabola, I know it has to be a minimum. Okay? 14 is the same. You don't need to do 14. We're going to take the first derivative of it, set it equal to 0. 15 gets a little more interesting. What's the first derivative of 15?
That would be 3x squared plus 12x plus 9.
Now, if I set that equal to 0, let's solve for x. It's the first thing I can do.
Take the 3 out of all of them, divide by 3.
Factor that.
So that would be,
Talk about factoring for a moment.
okay, yeah, I know we wanted to talk about that.
When you have a simple quadratic, and by simple I mean the coefficient of the x squared is 1, so that I know that it breaks up into x and x. The second step is determine what both your signs are. What do both the signs have to be?
Positive.
So plus plus, that's step 2. The third step is factors of 3 that add, because of that plus sign, to the number 4. Well, that's easy enough, 3 and 1. So that's the way I factor.
Okay.
Okay? So that tells me that there's 2 places on the x-axis where I have extrema. I've got an extrema at minus 3 and I have an extrema at minus 1. This is a cubic, so there's minus 1, there's minus 3. So this thing probably looks something like that. Notice that I have a relative maximum at minus 3, a relative minimum at minus 1. But I don't know that yet. In other words, all I know is that I have relative extrema at minus 3 and at minus 1. I don't know yet whether they're minimums or maximums. Well, to me, the easiest thing is the second derivative test. Take the second derivative of this. What do you get?
That would be 6x plus 12.
At my first extrema, what is the second derivative? Negative or positive?
It is it negative?
That means concave down,
Okay.
which means
So positive?
a local maximum.
Okay.
At minus 1, what is the second derivative?
It is positive?
That means concave up, meaning you have a minimum. Concave down means you're looking at a maximum. Concave up means you're looking at a minimum. And second derivative test, down equates to negatives, up equates to positives, if you're looking for a technique to remember it. Okay? So if the second derivative is positive, it's concave up, it's a minimum. Second derivative is negative, it's concave down, making it a maximum. There's also a first derivative test, which I actually find more complicated and I won't talk about yet.
Okay.
When you get to first derivative tests, you let me know, and we'll talk about it. In other words, well, I can talk a little bit about it. If I have a function that looks like that, and I realize that the slope of the tangent line is 0 right there, but is all that means is I either have a minimum or a maximum. Well, how do I know this is a maximum? It's because the slopes go positive, 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 positive to negative, 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 negative. If I had this scenario, the slopes go from negative, 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 negative to positive, 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 positive. So, on one side or other of the x-coordinate, if the first derivative goes from positive to negative, you have a maximum. If the first derivative goes from negative to positive, you have a minimum. So there is a second derivative test to determine whether your extrema is a maximum or minimum, and there's also a first derivative test. To me, the second derivative test is easier. It's easier to take the second derivative of that function and evaluate whether it's plus or minus than it is to determine whether the first derivative goes from plus to minus or minus to plus. Now, notice there's one other kind of function like that where I have a 0 tangent line right there, but I don't have, that's not a relative extrema, right? I don't have a relative extrema here.
Right.
Well, notice what the first derivative does. Positive, 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 0, positive, positive, positive. So if the first derivative does not change signs, you have neither. You don't have a relative extrema. You have a slope of the tangent line that's 0, but for it to be an extrema, the slopes have to change on either side of it. This function here would be y equals x cubed. The way I would graph that would be like that. Well, right there, there's a spot at 0 where the slope of the tangent line is 0, but it does not represent a relative extrema. And that's because the slopes go from plus, 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 0, plus, plus, plus. All right. $17 is really no different than 16. In other words, once you take the first derivative of a cubic, you have a quadratic. Quadratics all have two solutions. So when we take the first derivative of this and set it equal to 0, we're going to come up with two solutions. Let's do it. Let's do 17.
Okay.
What's the first derivative?
It is, let's see. Negative 4x to the second minus, let's see.
The way to do this is to take that exponent, make it a multiplier, and then what you have left over is 1 less. Well, so when I multiply this thing by 2, it cancels out with that 2, and I got just 21.
Okay.
X minus 5.
And then minus 5.
Okay. So that's the first derivative, and we have a quadratic. We have a quadratic that we can see goes like that because the coefficient is negative of the x squared term. But we're going to find out exactly where that peak occurs. We know it's a maximum, but I'll show you by the second derivative test also why it's a maximum. How do I solve that?
So do we want to take the second derivative, or are we?
No, we need to solve this. In other words, I need to
Okay.
figure out where on the x-axis that this function is equal to 0.
Okay. So we'll factor again?
Yeah. What's the first step if I want to factor? What should I do first?
This one.
It's very difficult to factor when you have a negative coefficient there.
Okay, so divide it all.
By
Divide
minus
each one
1,
by.
exactly.
Okay.
And that just makes that plus, plus, plus. When I divide the right side by minus 1, I still have 0. Okay? So now, this is what I call second degree factoring. Because the coefficient is not 1 here, I can't break it up simply into x and x. It could be 2x and 2x, it could be 4x and x. Well, I normally start with the factors that are closest together. I know the signs are plus plus. I know the only thing that can work is 5 and 1, and that does not give me a middle term of 21. So I got to go back and change it. I got to try 4x and x. That also doesn't give me a middle term of 21, but if I switch the 1 and the 5, it does. Now, let's talk about factoring. When I've factored a quadratic, I don't need to check the first term. I manufactured my factoring by making sure that this times this equals 4x squared. Okay? So I know the first term is correct. I don't need to check the third term. I manufactured my factoring to make sure that these were factors of 5. What I do need to check is the middle term. Always. Every time I factor something, I want to check the middle term to see if I got it right. Well, you get the middle term from the product of the inside terms and the outside terms. Well, the inside term is plus 1x. The outside term is plus 20x. Add those together, you get 21x. That is indeed our middle term. We have factored it correctly. And that's the only thing I ever check, is that middle term. But I check it every single time I do factoring. Because that's the one that's frequently what's not correct, is the middle term. So what are my solutions now?
They would be -5 and then -1/4.
Correct. So those are my two extremas. Do I have a way of telling which one is the max and which one is the min?
Can we do that by the second derivative test?
What's the second derivative?
The second derivative is 8x plus 21.
At this first point, what is that? Is that positive or negative?
Negative.
That means that is concave down, making it a maximum. What is it at -1/4?
Positive.
That means it's concave up, making that point a minimum. So not only can we tell where the extrema occur, but we can tell whether they're maximums or minimums locally by the second derivative test. 18 is essentially the same as 17. It's a cubic. The first derivative is going to give you a quadratic. That's going to give you two solutions. Those will both be your extrema, but you won't know which one's the max, which one's the min, unless you apply the second derivative test. Let's look at 19. It's a quartic. What's the first derivative on 19?
First derivative is 4x to the third minus 36x.
Okay. We're going to do what? Find the extrema.
Okay, so set it equal to 0, and then...
Now how do I solve that?
Would we want to factor again?
Okay. Is there a greatest common factor? That's always,
4x.
yeah, 4x. That's always your first question. In other words, rather than trying to factor it into two things, see if there's a greatest common factor, and there is. Leaving what?
X squared minus 9.
Does that factor?
Yes.
To what?
X, one will be plus, one will be minus, so...
That's the difference of perfect squares.
Okay.
So it factors into x minus 3 times x plus 3. So now there's three solutions to this, which we would have expected because we started with a cubic. What are the three solutions?
They are 0, 3, and negative 3.
There's your three extrema. Now, we don't know that they're all extrema. Because like I said, you can have a function that does this. Well, that's y equal x cubed. If I take the first derivative of that, I get y equal 3x squared. I set that equal to 0, and I come up with there's an extrema at x equals 0. And we can see by looking at it that there is not. Furthermore, if I apply the second derivative test to this, it doesn't help. It gives me 6x. Well, 6x is neither plus or minus at x equals 0, so the second derivative test doesn't help in this function. But I'm not talking about our function. I'm talking about this y equals x cubed. So just because we find a place where the slope of the tangent line is 0 at all three of these places, they don't all have to be extrema. One of them could be like this. It could just be a 0 slope tangent line that is not either a minimum or a maximum. It's just middle on the way. And this is where we need the first derivative test.
Gotcha.
And I'll go through that with you, just because if you haven't learned it yet, it's coming up next. Okay? So, this cubic function here, I want to know what's going on at x equals 0. Well, hold on. The first derivative test to see whether something is actually a relative extrema or not means the slope has to change on one side or the other of that coordinate. So let's take this coordinate right here and see what the slope does. Well, this is the first derivative, so this is the slope. When x is 0, what does the first derivative do to the left and to the right of 0? Does it change signs? And the way to determine, let's plug in -1 and +1 into this derivative right here.
Okay.
When I plug in -1, I get a minus, and a plus. We're multiplying them all together, so it's plus. So when x is -1, it's plus. What about when x is +1 on the other side of 0? Well, now I have a plus, a minus, and a plus. That's minus. So the derivative does change signs on either side of 0. And furthermore, it goes from plus to minus, which means it's a relative maximum. Hi. Notice that when I have a relative maximum, even if it's part of a function like this, whenever I have a relative maximum, my slopes go plus, 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 0, minus, minus, minus. Well, that's what this did. To the left of 0, it was plus. To the right of 0, it was minus. Therefore, at x equals 0, I have a relative maximum. You with me?
Yep.
So I know that that is a relative extrema, and I can actually call that's a max, a relative max. Now let's look at this point. Well, let's check either side of it. Because unless the slopes change signs, this is not even a extrema. So I have to apply this first derivative test. And in fact, they can't really ask you these questions, determine whether there's any relative extrema without applying the first derivative test. Because the first derivative test is actually needed to tell whether we're looking at an extrema here or we're just looking at a point where the slope is flat. Okay, so apply the first derivative test to this point. Let's go to the left. When x is 2, are we positive or negative?
We are negative.
Okay, so that's negative. Now when x is 4 on the other side of 3, what are we?
Positive.
Okay. So it did change signs. So it is a relative extrema. And for it to go from negative to positive, it must be a relative minimum. So this is a max, this is a min, because minimums go from negative, 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 negative slopes to positive, positive, positive slopes. And finally, let's check this last point, -3. Give me a couple of points to check.
We can do -4.
Is that positive or negative?
That would be negative.
And another point?
Let's do -1.
And actually, the closer you stay to this, the better. Because
Okay.
what if you have something like this? I got a lot of relative extremas here, but if I go too far to the right of that point, I'm not going to see the correct slope. So the closer you stay to that point, the better. So let's use -2. What does that give us?
That would be positive.
Which makes it what? A minimum or a maximum or neither?
That would be a minimum.
And these are all relative, meaning it's not absolute for the entire domain, but in that region, these are all relative extremas. And all three of them are. because they passed the first derivative test. And without that first derivative test, I really would not be able to say that all three of those are extremas. So all I could say is that the slope of the tangent line is 0 at all three of those spots. But slope of the tangent line being 0 doesn't make it an extrema. It has to pass the first derivative test also. So that was a quartic. So we know the first derivative is going to be a cubic, which gives us usually 2 relative extremas. Excuse me. That is a quartic. Quartics have at most 3 relative extremas. Quintics have at most 4. Cubics have at most 2. In other words, the most amount of extrema you can have for a function is always 1 less than the degree of the function. 20 is no different than 19. We're going to do it the same way.
Okay.
21, a little different. Let's look at 21. What's the first derivative?
These ones I always have problems with.
Okay, well, what's the first derivative of a constant?
0.
Okay, so we're really taking the first derivative of minus this to that. Always start with the exponent. 2/3 minus 2/3. Now write whatever's inside the parentheses and now put a new exponent that's this exponent minus 1. There's the first derivative. Ah, what did I forget to do? Forgot to apply the chain rule. The first derivative here is going to be the power rule times, in other words, the chain rule is the derivative of the outside times the derivative of the inside, right? That's the easy way to remember the chain rule. Well, I just took the derivative of the outside. I got to multiply it by the derivative of the inside, which is what?
3.
Gets rid of this 3 right there. So that becomes a minus 2. So that's the first derivative.
Okay.
And you're familiar with chain rule?
I am.
Let's practice it. Let's just make sure that...
Yeah, I think that's a great.
Chain rule is pretty easy. Let's do an example. If I want to take the first derivative of x squared plus 1, like that, the square root of x squared plus 1,
Okay.
well, I can write this as x squared plus 1 to the 1/2. So there's my f of x. Well, if I'm going to take the derivative of this, I'm going to take, what's the derivative of the outside? Start with the exponent, yeah. Times whatever's in the parentheses, and then subtract 1 from the exponent.
So negative 1/2.
But now we have to apply the chain rule because we have to multiply it by the derivative of the inside, which is 2x. Okay, so that's the chain rule. And the chain rule can be used multiple times.
Okay.
For example, well, the chain rule tells me that the outside derivative is, right?
Mm-hmm.
And now I have to take the inside derivative. Well, the derivative of sine of x squared is cosine of x squared. But then I got to take the derivative of that inside also, times 2x. So if I'm taking the derivative of that, I have to apply the chain rule twice. It's always the derivative of the outside times the derivative of the inside, and if there are multiple insides, you have to take the derivative of all of them, each one of them.
Okay.
Most of the time, the chain rule is just once. But let me give you some practice functions here. It's the derivative of that.
Let's see.
It's the derivative of sine.
Cosine?
So the outside derivative is that, but
Okay.
there's an inside also.
So 5.
So there you go.
Okay.
It's the derivative of that.
So first we would do it x to the third minus 1 to 1/2.
Okay, good.
Okay, and then it would be, let's see, 1/2 x to the third minus 1 to the negative 1/2 times 3x squared.
Good. All right. I didn't think you had the chain rule, so I was looking at this problem and I forgot to apply it. But let's see, which one are we working on here? We are on 21.
Yep.
So it was 2/3 to the minus 1/3, and then times 3, got rid of that denominator. So that's the first derivative. Okay. Now to find the extrema, I want where the first derivative is either 0 or undefined. Because if it's undefined, that could be an extrema also. In other words, if I have a function that looks like this, my derivative is undefined right there. That is an extrema. That is a relative minimum. But I'm not going to find it by looking for a derivative that's equal to 0. Because you can't differentiate at a corner or cusp like this. So the derivative at this point right here is not going to be 0. It's going to be undefined. Well, if I look at this function, is that function undefined anywhere? Well, that negative 1/3 puts that thing in the denominator, so that's actually minus 2 over 8 plus 3x to the 1/3. Now, is there a place on this derivative function that isn't defined?
So that would be when the denominator equals 0?
Yes. Which would be what? Minus 8 thirds.
Yeah.
When x is equal to minus 8/3, we have an undefined derivative. That's still a relative extrema. Okay? Is there any place where the derivative is equal to 0? In other words, where we would have a flat tangent line, which would also represent possibly a relative extrema?
That I'm not sure.
What makes that equal to 0? In other words, let's set it equal to 0 and see if we can solve it.
Okay.
Can that ever be 0 if the numerator is not? No, it can't.
No?
No. The only way a rational function, in other words, a quotient, a divisor by a dividend, the only way it's ever equal to 0 is if the numerator is 0. It has nothing to do with the denominator. It's only the numerator, and the numerator is -2. So it's never 0. So this can't be equal to 0. This only has one solution to it, and that is at x equal -8/3, the derivative function is undefined, which means the original function must have a corner or a cusp right there. And again, I don't know whether it's a maximum or a minimum. If this was my function, the derivative would be undefined there, and it would be undefined there. What I do know is that the first derivative test will tell me, because this case, the first derivatives go from negative, negative, negative to plus, 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 and in this case, the derivatives go from plus, plus, plus to negative, negative, negative. So if I check a point on either side of that, I'll know whether I'm looking at a minimum or a maximum situation.
Okay.
They don't actually ask in this problem whether it's a minimum or a maximum. They just want extrema. So is all we really need to know is that we do have an extrema at -8/3. We don't know whether it's a minimum or a max, but if it's undefined, it's one or the other. It's never undefined when you have that situation like this, where you have a flat tangent line right in the middle of the function. It's never undefined there. It's always undefined when you have a corner or a cusp, something like that. So when you find something that's undefined like this, you know that it is an extrema. We don't have to even apply the first derivative test to it to see whether it's an extrema or not. Whereas on previous problems we did. When we had 19 and we found 3 different places where the derivative was 0, we had to actually test each one to determine whether it was indeed an extrema. It might not have been. Okay, so we had to put it through the first derivative test. Well, here on 21, we didn't find any place where the derivative was 0. But we did find one place where it was undefined. Well, undefined tells you that, yes, that's an extrema. We don't have to apply a first derivative test to it. All right. I think you can kind of see whenever we have an exponent that's less than 1, that means by the time we take the derivative of this thing, we're going to have a negative exponent. A negative exponent means this is going to be in the denominator. We're going to have some places where it's undefined.
Okay.
This problem here is the same as this problem here. We're only going to come up with an undefined first derivative. We're not going to come up with any 0 first derivatives. Let's look at 23. Hold on. What's the first derivative of 23?
Is this another one where we use the chain rule?
No. When you have the addition of two things, you don't need the chain rule. The chain rule is usually when you have a composite function. A composite function is the combined functions. In other words, when Let's talk about that for a moment. When I have f of x equals the square root of x squared plus 1, that is a composite function. What I really have are two different functions there. I got a g of x that is the square root function, and I have an h of x that is x squared plus 1. So if I want g of h of x, that gives me f of x. In other words, g of h of x, that's what they mean by a composite function, would be the square root of x squared plus 1. So when I'm looking at a composite function, I know I have to apply the chain rule. In this case, this is not a composite function. It is merely the sum of two functions. If f of x is equal to 2x plus 3 times x to the 2/3, I can just take the derivative of this and add it to the derivative of that. In other words, the derivative of the sum is equal to the sum of the derivatives.
Okay.
Not true with products. The derivative of two products, a times b, is not equal to the derivative of a times the derivative of b. We have to apply the product rule. Okay? So it's not always what it seems. But when you're dealing with sums or differences, it is. In other words, what's the derivative of this part?
2.
And this part?
Is it 2x to the 1/3?
The minus 1/3.
Minus 1/3, okay.
Yeah, and that matters because this looks like this. Putting that x in the denominator. When the x is in the denominator, that means we're going to have places where this function, the first derivative, is not defined. And wherever the first derivative is not defined, that's an extrema. So when x equals 0, you have an extrema. And we won't worry about whether it's a minimum or a maximum yet, because it doesn't look like you've gotten to that part of calculus yet. But we do know it's an extrema. And we also know that there's no other place, if I try to solve this for equaling 0, there's no solution.
Right.
I need a numerator to be 0 for this thing to be 0. Or actually I need this to be able to be minus 2, and it never can be. Hold on a moment. Take that back. That's not true. Let's see. First of all, I know that x is an extrema. X equals 0 is an extrema, because that makes this undefined. Is there a solution to the rest of this? In other words, when I set the first derivative to 0, do I have a solution? Well, I think I might. If I move this 2 to the other side, I get minus 2 equals 2 over x to the 1/3. Now I can multiply both sides by x to the 1/3, so I have minus 2x to the 1/3 equals 2, which means x to the 1/3 equals negative 1, which means x equals negative 1. Aha! So I do have another spot on the curve where the first derivative is equal to 0. So I have two places. I have x equals 0 is undefined. That means it's an extrema. And I have x equal minus 1 gives me a 0 slope, which may or may not be an extrema. Let's figure it out. Let's apply the first derivative test to this function right here. about minus 1. Better yet,
Okay.
since I've taught it to you in this session, let's apply the second derivative test to it. What's the second derivative of this function here? Here's the first derivative. What's the second derivative?
It would be negative 2/3 x.
To the minus 4/3. Don't forget to subtract that 1 from the exponent.
Right, okay.
Okay? And so this is the second derivative. We want to evaluate it at this point, minus 1, which we're not sure is an extrema or not, because all we know is it just has a 0 slope. Well, what is the second derivative, plus or minus, at minus 1?
It is plus? Or is it
Wow,
negative?
boy, that's a very good question. This is another 2 hours of mathematics, but you cannot take a negative number to a fractional exponent,
Okay.
which is a whole nother thing altogether, but you might think you can. In other words, it might look like you can do this, right?
Right.
Because the cube root of negative 8 is what?
2.
Negative 2, and negative 2 squared is what?
4.
So it looks like that's the answer, but it's not. You cannot take a fractional exponent of a negative number. Okay, just remember that that's a rule. It's not easy to explain. It's pretty higher mathematics, higher than calculus. But you cannot take a fractional exponent of a negative number. And in order to evaluate the second derivative here, that's what I have to do. Here's the second derivative, but I need to plug in minus 1 for x. So I can't use the second derivative test. I could use the first derivative test. So I would evaluate what this thing does on either side of minus 1. Well, when I plug in 0, it's 0, no slope. So let's not, ooh, boy, I can't even plug in a number to the left of minus 1. I can't, oh, no, that's the second derivative, not the first derivative. Even the first derivative doesn't evaluate with a negative x. Wow, I don't know what to do here. Yeah, I mean, I guess for this problem, you're going to say that the extrema occur at x equals 0 and x equal minus 1. But quite honestly, I'm not sure how we tell if minus 1 is an extrema or not. I can't evaluate the first derivative to the left of minus 1. It would require me to take a negative number to a fractional exponent. So I'm not quite sure on this problem what we're going to do.
Okay.
All right, but we got quite a bit covered today.
Yeah, you did.
All right, Molly, I will talk to you next time.
Okay, thank you so much.
You're welcome. Bye-bye.
Bye.